Mike here. We're going to go ahead and start our first lecture in Chem 130, our scientific thought and matter classifications. So one of the things I usually like doing is having this question put out to a large audience is why science? And what we see here has varying kind of results depending on your perspective, be you a pessimist, an optimist, or what we're potentially introducing here, the scientific view. So what I'd like you to do is take a second and kind of write out real quickly what you think a pessimist and optimist might say. And yeah, that means you should pause the video because you'll get these periodically telling you to pause and try and write it out. That would be the space bar. Just push that button just once. Okay, so theoretically, based on past experiences, we might get people going through and saying that, say, a pessimist sees a bunch of strawberries. Okay, and you might say, well, wouldn't the optimist say the exact same thing? Well, yeah, they could potentially, depending on their perspective. So potentially the pessimist sees strawberries because they're allergic to them, whereas the optimist really likes them. The scientist may very well see strawberries as well. So then what kind of frames each of these responses? Because it's the same answer that we're writing for these, but there's a different context or meaning behind it. Remember, the pessimist said strawberries because they were allergic, right? That context changes our interpretations of it. So we've got an allergy, okay? Optimist says because they like them, okay? Or I'm just going to say good. But when a scientist sees this, he's not saying good or allergy or bad necessarily. He's looking at it and saying, or she's looking at it and saying that those strawberries may not fit a certain level. So they could go into the biological realm of what makes them a strawberry or something else. But what I would argue scientists are actually doing when they look at this is not so much that they're strawberries or the pieces behind us, but they're saying that they can do that better. They can make a better strawberry. They can make a better strawberry pie. So when we're looking at strawberries as a scientist, we're probably saying that those were out of season, okay? And that we can make it better, okay? And we can make it better by finding in-season strawberries, okay? We could go to the heart of California and pull them from an organic farm there and get really good sweet-tasting strawberries. So really what the scientist is doing with any observation is looking at it and saying, I can do better, right? And that process of being able to say that I can do better is largely what makes scientists look like egomaniacs, which is kind of true, right? But really their motivation behind why they think they can do it better comes up to the real debate on deciding whether they're bad egomaniacs or good egomaniacs. And even then, that bad and good is all relative. Right? But what scientists are ultimately trying to do is to study the world around them because they feel that they can contribute and understand it, and with that understanding can make things better. The motive behind that, we won't worry about, okay? But that's our goal. How do we make things better? Right? And the first process behind making things better is outlining the process by which you go through and make that better. Right? And so what we're trying to do is learn that something new, right? But we have to have a clear process behind it. That clear process is usually referred to as the scientific method. And even then, when we're thinking about the scientific method, what we're actually referencing is not just the scientific method, but proper note-taking. Being able to take good, clear notes or useful notes is what's going to help us be able to go through and process and stepwise through science. Once we have that good step process, what we'll now move into is what are those processes behind the scientific method. And the first one that typically gets put out there is observation. And we'll qualify that in a second. After observation, we usually come up with a hypothesis. That was a strawberry pie. I can make that strawberry pie better. Okay. Once we have that hypothesis, we'll then go through and design an experiment. Okay. That strawberry pie wasn't particularly healthy, and so I'm going to make it better by using a whole wheat flour to make that crust instead of just white flour. Okay? What people who haven't made pies before might realize or not understand is that that doesn't make the pie better. Okay? It actually ruins the crust. Okay? And so one of the big things that comes out of the scientific method that people really don't often see is that the end result of an experiment isn't this conclusion and now we've got these big grand results that we can then publish and we become famous. It isn't that. It's actually failure. Okay? Our experiment utterly failed. Okay? And there's a variety of reasons that failure comes in. Okay? And this is why I think students struggle with science. 90% of the time, what we do in science is fail, and usually fail pretty miserably. Okay? What makes science so fascinating and cool and exciting is that we just try again. Right? We go back to it, we create a new hypothesis, we design a new experiment, and we run it again. 90% of the time it fails and we loop back through. Okay? If we look at the strawberry pie, we've contributed through history to the creation of that strawberry pie. So we know what flours are good, what sugars are good, what strawberries are good. And when we go to look up a recipe for that, we trust that that recipe has that history behind it. We aren't just picking some random recipe that says pick rotten strawberries up and throw them in because they taste good. They probably don't. Right? So we're relying on that past note-taking to build us forward. Right? And that's what we're really trying to get in this. And so we do encounter failure a lot in science. Why do students freak out so much with this? Right? And arguably most people. Well, what they don't see is that scientists fail. Right? And that's a challenge. We read through the textbook and we're like, oh, dude, this dude just discovered the atom. No, he didn't. He based it off of hundreds of years of science and knowledge that allowed him to draw those conclusions. Same thing with the recipe. The recipe we could churn over pretty quickly and we could test that out. And by the end of the day, if we just redeveloped the building of a strawberry pie, we could probably do it in a day. Redeveloping the discovery of all of chemistry isn't going to happen in a day. Okay? And it's that failure process that you don't quite see until you really dig into it. Okay? So realize this class is going to encounter tons of failure. Okay, on multiple levels. What you need to do, and what I'm going to try and help you do, is to get through that failure by adjusting your process so that you can go beyond just the experiment of the class and you can end with a scientific theory or a natural law. Okay, and these are the conclusions that come out of successful experiments. Right? And we can build knowledge from those and we can continue progressing. Right? And that's ultimately where we're trying to get. So again, a quick walkthrough. Observation, we're just seeing. We're using our eyes, our nose, our hands. We're using whatever kind of feel or touch that we can get a hold of to try and recognize what we're seeing in the world. We then create a hypothesis on which to learn why that thing was happening. We then build an experiment to test that hypothesis. Right? That experiment usually ends in failure. But once we have that experiment done, we can then evaluate it. And if it was deemed successful, that's where we kind of run into these theories. And a theory is a slow progression of knowledge that works with the information at hand. So we continue to work with it. Science has 800 years of knowledge building towards these theories. And so our theories are pretty solid. It's not just a random, oh, I just thought of this. These have 800 years of scientific knowledge backing them up. The natural law is kind of the be-all, end-all. There isn't anything we can do to counteract that. Right? It's not a theory per se because it's always true. The theory could have holes in it where it doesn't perfectly describe the system that we're looking at. Okay? So where does chemistry fit into this whole science process? Well, every field that you're going to go through and talk to is going to say that they're the bridge, but really they're all wrong because chemists are the bridge. What we end up with is kind of mathematics and physics, the hardcore kind of cerebral, I'm just playing with numbers to describe random stuff because I want to do it, and physicists who took all of that weird cerebral mathematics and were able to make sense of it And then at the other end of that bridge, we've got all that hardcore kind of application. This is where you get biology, engineers, my opinion, are out on that other end. Those are that hardcore kind of, not even hardcore, they're the application side of science. And chemistry's role is really to bridge those two areas. That very cerebral, I'm dealing with mathematics and theories and all sorts of crazy stuff like that, to the how do I use this? What am I going to apply it to? How is that going to build to make my world a better place? And depending on the field that you're in within chemistry, you're going to be at different aspects or different lengths of that bridge. And what we're looking at in fundamental chemistry is what some would argue is general chemistry. It's just the overview, the overarching principles that touches on everything so that you really learn nothing or something about everything. As you continue through chemistry, if you so choose, what you'd be building into is looking at each of these individual fields and deciding what their particular application was into that further distancing down the road. Okay? So within those fields, we get organic chemistry, which is the study of carbon and hydrogen and all of its different roles and changes. Biochemistry, which is really just an application of organic chemistry, despite what biochemists might tell you. Biochemistry is looking at how those carbon and hydrogen molecules that were played with and studied in organic chemistry are built in biology, in the natural world. Inorganic chemistry is looking at pretty much everything else on the periodic table, which is a lot, and saying how do those different atoms and molecules interact with each other. And then physical chemistry, as the name kind of suggests, looks at the physics and mathematics behind this whole process. Okay, so chemistry's role kind of bridges those two big gaps, and then it subdivides out into those individual categories where we're studying the different aspects in much smaller chunks. Okay, so to observation, we get qualitative and quantitative. So we've got this cute little picture here. So this would again be one of those opportunities where we could hit that space bar, pause the video, and think about our qualitative and quantitative observations. For those of you wondering what's actually going on right here, I was waiting for you to hit pause. For those other people that hit pause and came back and were like, did I hit pause? Yeah, you probably did. Qualitative and quantitative. These are our two types of observations that we get. Right? In our qualitative observations, what we're looking at is kind of the quality of our observation. Okay, and the quantitative, we're looking at the quantity. Right? The quantity tends to be a little bit more straightforward and explicit, so we can stick with that one. Our quantity would be looking at numbers. Okay? And that's what most people put on science. Okay? And it's that mathematics side of the quantitative observation that is critical to going through and kind of ranking and organizing systems. But it isn't the most important. For instance, if I was, I don't know, a tailor, and I looked at this picture, I might see that there's a lot of wool there and it looks kind of dirty, and that's going to make kind of a crummy suit. Right? So I'm looking at the quality of the wool that's being projected here, not necessarily the quantity. Is the quantity going to become important? Probably, because how much wool am I going to get to make a suit? Is it going to be enough? Right? So we're looking at that kind of balance between our qualitative, which is those big kind of quality observations. So when we're thinking about it, we're thinking, how good is it? That taste, those are almost emotional aspects. The quantitative are those quantity and numbers, right? And even then, we have to be a little bit careful with our quantitative. It's not just numbers. Because if I just tell you 18, that doesn't mean anything until you actually label that 18 with. And maybe we could put in 18 pounds. Say there's 18 pounds of, I'm not a herdsman, 18 pounds of usable meat. Based off a previous class, I don't think it's 18 pounds. I believe I was told closer to 70 pounds of usable meat that you could get off of probably this sheep. And so that is going to change our perspective. Right? So what we're thinking about when we look at science is recognize that there is two aspects, qualitative and quantitative, and that we usually very heavily overemphasize the quantity, right? Don't push to the quantity all the time. Recognize that you should be looking at the quality of your observations as well, not just that quantity. So, qualitative observations, the easiest ones to start with. So, qualitatively, what do we have quantitatively? 70 to 80% of the composition of life, right? That special substance is water, okay? Or what we might reference in a chemistry lingo as H2O, or dihydrogen monoxide. Feel free to search the internet for dihydrogen monoxide. You can find some interesting things, right? And water has an interesting principle for us, or an interesting aspect that we can play with here. Water is one of the few substances that on this planet we get access to all three phases, right? And we can make qualitative observations about solids, liquids, and gases and see how they interplay and relate to each other, right? And that's where we could be looking at things like shape, volume, and compressibility. So these are qualitative observations that we could use to classify the different phases that we could interact with, because we've got the solid, the liquid, and the gas. The solid and the liquid, perhaps the earliest labeled and identified. The liquid took a little bit long, or the gas took a little bit longer, because that's harder to grab a hold of and see. But what we're looking at is trying to rank these things out according to shape, volume, and potentially compressibility. When we think about our shape for our solids, right, they're static, right? They don't really change. The same thing for our volume, static. These are really kind of unchangeable substances. And when we go all the way to compressibility, they're also pretty static. So compressible means how do we shrink them? And you might have a hard time recognizing that. So let's go through and look at it at a really, really tiny scale. Let's say, boom, there's an atom. To have a solid, I have to have a bunch of these pieces. If I'm looking at a compressibility where it doesn't compress, that means these would need to be stacked very closely to each other. And because they are very close to each other, there's hardly any white space, which means I can't compress them. Okay? What happens when I move to a liquid? Well, in the case of the liquid, the shape, okay, flows, okay, it changes, right, or is mutable. The volume, however, is still static, right? It doesn't really change. Compressibility, usually same deal, static, right? There's a little bit of compressibility, but not much. So if our shape can change, so if I looked at the solid, they're all rigidly lined out, what's going to happen with our liquid? Okay, well, our liquid's probably going to have a little bit more kind of sections moving on with this. And one of the interesting things here is it's going to take the shape of our container. So our container is going to kind of mutate that shape a little bit. Because it's a free-flowing shape, it could move kind of anywhere. What happens if we move then all the way out to the gas? Well, now the shape becomes really mutable, okay, or very changeable. The volume also inherently mutable. Compressibility, extreme. Okay? So if we're going to look at this, this is where our container becomes really important. Because if we're going to now draw our box to represent our container, and we're going to look at that gas, if I'm going to draw a gas particle, I get a lot of compressibility, which means there's a lot of empty space between those. So I'm going to have to move so that I've got massive amounts of empty space in between these so that I can extremely compress them. Right? How is that also going to affect things? Well, if I have all that empty space, that means the volume is going to be pretty drastically different too, because those particles are going to move away from each other as much as possible. Right? And that's going to mean our volume is going to take whatever the volume of our container is, not the particles themselves. And the shape's the same deal. The gas particles are going to free flow wherever they want, regardless of the shape of the container, or to the shape of the container rather. And so what we've got are ways that we can classify solids, liquids, and gases that allow us to come up with some kind of qualitative simplifications for those individual phases. And that's kind of a neat process. Right? If we now push this further, well, our solids, liquids, and gases are all kind of a piece within our matter. So solids, liquids, and gases are all inside this. Okay? And what we would then do is kind of divide these things out. Okay? We get two primary categories: mixtures, which are spatially linked, and then pure substances, which are chemically linked. Okay? That I've always had a hard time with, because we've fundamental chemistry class, and what are we, 10 minutes into the class, and we're defining a substance based off of a word that we haven't defined, that chemically linked. Okay, this is the first time I've ever attempted to do this, so I'm probably going to do it poorly. How does it work with the thumb? Like the thingy, and you slide and you're like, oh my god, the thumb's not connected anymore. I'm just going to pretend I'm doing it right. Woo, magic, right? Right? If that was actually happening, for those people that don't know what I'm talking about, don't worry about it. Okay, that would be crazy, because your thumb is chemically linked to your hand. And so in a magic trick, if it appeared the thumb popped off, oh my goodness, that would be crazy, because it's chemically linked to your hand. Okay, but if it was spatially linked, like, I don't know, my shirt, so if the shirt started coming, I'm not going to do that. Okay, you'd be not really surprised. You'd be like, yeah, the shirt can come off. That's not a big deal. This is a class, so you shouldn't do that. And you're surprised for different reasons. Okay, that would be kind of a spatial linkage. It's not physically or chemically connected to me. It's loose. It could theoretically come off, right, under the right circumstances. The chemically linked, your thumb, if that comes off, that's not a good thing. Okay, that takes a lot of work to put back on. And so that's really our big difference between mixtures, which have that spatial arrangement, and pure substances have a chemical connection. Each of those categories can then divide out again, right, into two different kind of systems. Right? So let's go through and look at we'll look at the mixtures. We're going to do heterogeneous and homogeneous. So hopefully you've heard those terms hetero and homo before, and that's why we kind of pulled those out to get kind of that root language. So hetero is referencing two or more, okay, two or more types. And then the homo is really just one type. Okay? And well, what is that type? Well, what I would argue you're seeing there is two or more phases, or one phase. Okay? And that one phase is going to become tricky, because solids, liquids, and gases isn't going to cut it anymore. So let's take a look at our heterogeneous, two or more phases. Okay? So I'm looking for that visible separation. So I could take sand and I could take water. And if I mix those two together, they are now a mixture, and they are spatially linked because the water is now with the sand. But is that a heterogeneous mixture or homogeneous? Okay? Well, the sand will all settle out. It doesn't dissolve in the water. So the sand will stay a solid, and the water will stay a liquid. We can visibly see that there's two phases. So we have a heterogeneous system. So sand and water works out really well as a heterogeneous system. So let's make it a little bit more challenging. Let's talk about, let's say, oil and water. Right? Well, oil and water becomes a little bit trickier, because oil is a liquid and water is a liquid. Right? So if we're thinking about this, isn't this just one phase? It's all a liquid. Well, can you see a visible separation between those two liquids? Yeah? Then that's a heterogeneous system. And so oil and water, like salad dressing, is a heterogeneous system. There's a visible separation. Okay? And now I'm going to throw my favorite one into this, fog. Okay, which I know is a weird system to be referencing in the state of Arizona, but fog is kind of this weird misty stuff that we see in the sky, and it turn on your high beams, you can't see anything because the light reflects back and becomes kind of a hazard. Should that be heterogeneous or homogeneous? Well, we addressed heterogeneous, but we haven't addressed homogeneous yet. So let's take a look at homogeneous. Homogeneous says no visible separation. So what happens if I say take salt and water. Well, salt is a solid, water is a liquid. If I mix the two and I still see solid salt, then that's heterogeneous. But feel free to test this at home. Add a little bit of salt to water and shake it up. What happens to the salt? It dissolves. And I can no longer see it in the water. Right? Add to this that if I drank water from the top, it's going to taste salty. If I drank water from the bottom, it's going to taste salty. That salt has dispersed itself through the entire container of water. Okay? So there is no separation between salt and water. They have homogeneously mixed. So now the issue, I don't have a solid, I don't have a liquid, because both of those things refer to pure substances. The homogeneous phase introduces a new phase. In this case, it would be called aqueous because it's dissolved in water. Really what we're talking about with our homogeneous is solutions. It does not have to involve liquids, but it typically does. Right? And so these would be solutions. Other things, think about air, right? Which is going to be nice shifting over to our fog. What do we know about air? Well, in air, there is CO2. Also in air, we have oxygen. That's how we exist and breathe. So CO2 and oxygen are existing at the same time in air. Right? There's also nitrogen. There's also some sulfur compounds, particularly if you've had some beans. Right? So there's tons of things in air, and we can't visibly see that separation. Right? Which means air is a homogeneous mixture. Right? In this case, it's all the gas state, not a liquid solution. So our homogeneous doesn't have to be liquid. Gases typically also form homogeneous solutions. Which then takes us to the next question. Fog. Well, what is fog? Right? Fog, as we kind of alluded to, really only happens in places where we have lots of water and it's cold enough. Right? So what's going on with that? Fog is water in the air. Right? So it is a mixture of both water and air. Does that make it a homogeneous mixture or heterogeneous? Well, believe it or not, there's water in our air right now and we don't see fog. Why not? Because the water in our air right now is in the gas state. The water in the air when we have fog is a liquid state. Fog is the combination of liquid in gas. That's two phases. Because it is two phases, that is now a heterogeneous system. For those people being like, but I can't see the visible droplets, you're right. Visible's in quotes for a reason. Visible separation becomes a challenge to kind of nail down. How do we evaluate that separation? Remember, we talked about it also when we said we turn on our high beams in fog. What happens? The light reflects back. Why is it reflecting back? Because it's hitting a different phase. It's that phase of the water droplets causing the light to reflect back at us, and that's why fog is, again, a heterogeneous system, not homogeneous. Tricky one, I know, but I like it because it's a cool little example. Okay. If we move over to the other side, we've got our pure substances, which are chemically linked. These are our compounds and our elements. Right? Compounds require at least two elements. Elements are only one type. Right? So remember, this one started with chemical, which is problematic because we haven't defined what chemical linkage is, other than breaking my finger off of my body seems chemical. And then compounds versus elements. Well, I'm now bringing in two more words that I don't know. And one of those words, compounds, I'm using the other one to define it with. That becomes questionable. Okay? So to kind of put this all together, our elements are the smallest smallest kind of piece of a particular type of substance. Okay? I can chemically link that to another type of element, and now I have a compound. Right? So it's a larger structure. I can link that with a whole bunch of different things. So for example, if we looked at water, which we said was H2O, what I've got within that is two elements, hydrogen and oxygen. And I have two hydrogens. The two refers to what's in front of it, two hydrogens, and then only one oxygen. Well, how many oxygens do I know? Well, there's an implied one there. If I were to look at an element, I could say hydrogen was an element and oxygen was an element. Those could be pulled out of the compound to look at their own level. Right? Which gets us to the next big slide here. What are our elements? So these are our smallest pieces, and those become important to us because what we're looking at with our elements is kind of our core for chemistry. And I'll get to that in a second. Oh man, that's where we get our periodic table of elements. That's what all those things are. Okay, so what we've got here, and we'll see a slightly better one in a little bit, there's 118 different elements. You are not required to memorize them all. You are required to memorize some. That's where that elements for memory document is coming into play. Right? But what we're going to start to do is recognize that there's patterns and categories within the periodic table that allow us to understand a little bit about these elements without actually having to grab a hold of any single one of them. Right? That first classification is looking at our metals, metalloids, and nonmetals. Right? So we've got these solids, liquids, and gases. We also found that we could define things according to these other categories. Right? So we noticed that metals tended to be solids. They were almost always shiny. Right? When we hit them with a hammer, they just kind of deformed. That's malleable. Right? When I put a match up against them and I touched the other side of the metal, it got hot. Right? Heat passed through the substance. Right? And we noticed that that happened also with electricity. Okay? And then we started to do some other kind of observations that require some measurements, and that's looking at our densities, our melting points, and then we also noticed something about their reactivity, their chemical properties, that they reacted with nonmetals. Okay? So we noticed that there were a group of elements that had these characteristics, so we could call them metals. Why metals? It was fun. Right? We also noticed that there were some other elements, not as many, that didn't share these properties. Right? They were gases, right? Or they were dull. They didn't shine. They were just kind of flat, matte-looking structures. When I hit them with a hammer, they shattered instead of just deforming. Okay, so there's the brittle. When I added a heat, put a match up underneath one, I could touch the other side, and I didn't really feel anything. Okay, so they didn't allow for the conduction of heat or electricity. Okay, and then when we started to make observations about how they interacted with things, densities and melting points were also different. So because we saw these different categories, we decided to classify them. And what we ended up with is really just category A and category B. Okay? But we just called category A metals, and we called category B nonmetals. Right? And that was neat. When we started to put it into the periodic table, we noted that they had to interact somehow. And the threshold on which we changed from metal to nonmetal, we called metalloids. Right? And the metalloids aren't just on that threshold. It turns out that their physical properties and their chemical properties share a little bit of the nonmetals and share a little bit of the metals. So they have that kind of blend back and forth. So that's kind of neat. Right? And that's what's going on with those. Okay, so if we're going to go through, we got some pictures here. These are all kind of shiny. These would be our metals. Right? If we took a look here, notice here, these don't really have that same shine. These are some examples of nonmetals. Okay, and you might be going, wow, what's that pink colorful one? Well, that pink colorful one is actually just a clear gas, but if you pump 20,000 volts through it, it shines a bright light. Cool. Okay? Most things, when you pump 20,000 volts through them, believe it or not, shine a bright light too. Right? I don't recommend testing it because it's usually the end of whatever you're testing. But if you had, say, neon signs, that's what's going on. We've got a liquid in there with bromine. Right? So we've got characteristics of our nonmetals. If we go through and look at these pictures, this is me just being obnoxious. Well, these are shiny and they're solids. Okay, well, because they're shiny, we might say that they're metals based off of the only evidence we can really pull at, their phase and that shine versus brittle or shine versus dull. We might call them metals. But it turns out that these particular substances, that when you hit them with a hammer, they don't deform, they shatter. Right? So they're solid, they're shiny, but they're brittle. Right? That's kind of weird, right? Because if we said solid and shiny but brittle, that's not all the same property, right? That's a little bit different. And we noticed that they actually didn't conduct electricity very well either. Right? So we're starting to get a blend of both of these categories. Right? These are examples of metalloids. And really, you're not going to be able to differentiate our metalloids unless you're given this kind of data set of how we could differentiate our metals and nonmetals. Right? So these are all physical properties that you should be aware of, so that if we said what classification would best match a substance that was malleable, not conductive, with a high melting point, and reacted with everything, right? You should be able to recognize that that was a blend of both categories, and so we're probably talking about a metalloid. Okay, so it's a really easy multiple choice test. I do think it or multiple choice question, I do think it does kind of suck because you'd have to have these things memorized. P.S. We're in an online environment right now. Hey, you could probably have this slide handy to answer those kind of questions. So here's our elements, right? You should be memorizing some of these. And for people being like, well, memorization is stupid, we shouldn't have to do that because we have access to all of this information. Yes, you do, right? You also have access on how to start your car every morning. It's in the user's manual. When was the last time you referenced the user's manual? You haven't? Okay. There are some things that make sense to memorize so that we don't have to constantly relearn. Okay. That's what's in that elements for memory document. So when I'm telling you to memorize something, it's because you're going to be using it again and again and again and again. And if you don't memorize it, the time it takes you to figure out the answer goes through the roof, and you end up not doing very well in the class. Those people, well, the real world's not like that. Go to your doctor, okay? And if the doctor told you after you sat down and talked with them, they're like, look, you know what? You've got some interesting symptoms. I'm going to take a look at these symptoms and get back to you in 2 months. I'll let you know what I maybe find. You're probably going to find a new doctor. You take your car to the mechanic. They're like, yeah, we'll hold on to your car for, a month and maybe it'll be fixed. You're going to find a new mechanic. Okay? So those stages of experience are things that you need to be going through. So when I'm telling you to memorize something, it's for a dang good reason. Go ahead and take advantage of that. This periodic table has all the names on it, so you could study from this one. The periodic table that you will likely be seeing on your exam will look something like this. So there's a bunch of stuff within it. Note that sometimes the numbers change a little bit. I would recommend you use the exam periodic table for your studying processes. And yeah, so you'll be expected to know some of these elements and be able to know what that information is that's stored within it. It'll take a little bit of time. So don't immediately try and memorize any numbers. Right now, name and symbol. Keep it at that. Get used to knowing where it is on the periodic table, because that's helpful. Know where your tools are before you start. Okay, and with that, we've gone ahead and finished our very first lecture. If I can figure out how to stop